I guess some of you think, looking at this title now, it's a bit of marketing now, running 1 million cores as HPC in the cloud. Well, if you think it was marketing, thanks for coming anyway, because it's not marketing. We actually had one customer that was running a single cluster on AWS. They use Docker images, they put them on Amazon ECR, and they run them as AWS batch. So it was one single cluster. And what I like a lot is they used spot instances. This means that you save like 70 to 80% for running the whole computation. And the computation that normally took them like 3 weeks, it went down to 8 hours. That's a lot now. So using HPC in the cloud is not marketing at all. It's innovating, it's accelerating your time to innovation. Now, the question is, what would you do, obviously, with 1 million cores in the cloud? And I have a customer here on stage later. They're not using 1 million cores, but they will tell you about their application of HPC in the cloud. It's Sebastian Wasilewski. He'll be on stage later with me and tell you about the real application of HPC on AWS. What I want to do is I want to give you a brief overview, a brief introduction. And this is actually a level 300 talk, which means it's meant for people that have some familiarity with the topic and that may or may not have direct experience implementing a similar solution before. So my name is Munz. I'm a technical evangelist for AWS. I typically cover the German-speaking countries, which is Germany, Austria, Switzerland, as you might know. And I'll give you a tech overview, and then we switch to Sebastian, who's talking about the real-life application. Now, I assume that you've been around in HPC, and this is why you're here. Or that you may be very new to HPC, and this is why you're here. Either way, you probably know this. This is the best way to solve most problems in HPC. And if you've been around in HPC for a while, you get this, because this is like a long-running joke. No, and if you have a computer science background, you know Amdahl's law that says the processing power kind of doubles every 18 months. No, so the best way to get a speed up of 2 for your application is, well, to go surfing for 18 months. And then 18 months later, you come back and you have this speed up of 2. And the question is, why is it not working? No. Why do I see so many PhD students that work for 4 years and then they try to adapt their application to a HPC computer, and at the end what they gain is like 4% or 7%, and that's the result of 4 years working, like adapting your application to a machine that already exists. And so why is it not working? Why is this surfing thing not working? Well, the answer is because you don't get the new hardware if you come back. No, there is no twice. There's no processors available for you that are twice as fast if you buy a classical HPC machine. So if you're in the old world, you buy such a supercomputer for tens of millions of euros, and it will be running like 4 years probably. And to get access to this supercomputer, you need to write an application. And I did this myself when I was younger, and I was rejected, no. And they said, no, we have more important people that are completely keeping this supercomputer busy. And those people, they always keep this supercomputer busy. And you know why? Because they do scientific computing, and all they need to do is reduce the grid, and then again, they have like 4 times more compute requirements. So this machine will always be busy throughout those 4 years. And if you're a junior like I was, you just don't get access. Even if you're happy to pay for it, you wouldn't get access. So it's hard. And then if you get access, you probably have a number of questions that you want to run as batch workloads, and the parameters you want to change them a little bit, you want to play with them, but the machine has a fixed size. So running various questions, you have to run them sequentially on this highly, massively parallel computer, because it has a fixed size and the size is kind of limited. And if you switch to the cloud, all this is very, very different. So you don't worry anymore about these millions of euros that you invest for the supercomputer. even if you don't write this application now for getting compute time, you can just go to AWS and start today. And I'm going to show you some services that make it super easy to set up your own HPC environment. So it's kind of democratization now of HPC. Because if you spend this $100 that might be the cost for such a huge, complex simulation, you're happy, you can do it anytime. And if you need to run this several times with different parameters, there is no fixed capacity. There is no one single HPC computer in the cloud. It's actually, you can run as many parallel batch jobs as you want to do. So the technology is the thing that is kind of not making this surfing joke work, no, because you don't get the new technology after 18 months if you buy the computer, the HPC computer for 4 years. If you go to the cloud, we actually work really, really hard to give you the newest technology, the newest kind of Intel processors, and the newest software, and so on. And this is why, surprisingly now, this joke would actually be true. It could work. So what we want is that you focus on innovation instead of doing the heavy lifting and adapting your applications to the HPC computer that you have on premises. We want to give you choice. And this is kind of a rough overview also of this presentation. If we look at compute, this is actually the center of running your HPC workloads. It will be those EC2 instances. And in this presentation, I want to point out like 3 very important ones, special ones that you should know. And there is different options for storage. You know that we have file system, EFS, we have block storage, EBS. We have the object storage, a blob storage, where you can store any amount of data on S3. And there is a new file system, HPC class file system now, that is called Luster. And I want to explain you a little bit about Luster later on when I talk about storage. Then networking is vital, it's core. It kind of determines if your application is really running in a good way with a good speed up in parallel. So networking is critical. Networking bandwidth are improving if you look at the classical EC2 instances, and I want to go in a little bit more detail. But even more important, we have a HPC class network now, and I want to go into more details later when we come to this. Then it's automation and orchestration. It's AWS Batch and AWS Parallel Cluster that are important to point out. And at the end, you want to virtualize your results. I'm not going into more details here. Now, looking into the platform choice, as of today, we have 190 different instance types and configurations. And here we want to talk about scientific applications, about HPC. But very often these instance types often make sense for people that run business applications. Like in the summit that we had in Berlin, that was end of February, we announced that you can now run the biggest in-memory cluster for SAP applications. The in-memory database is called HANA, and you can have 48 terabytes of in-memory database. So the same instance types, obviously, they work both ways now. And 48 terabyte is a lot. It's RAM. No, it's not disk storage. 48 terabyte of RAM, and that's the biggest commercial in-memory database that you can run, and you can run it on the AWS cloud. And some other instance types I want to pick out and explain you in a little bit more detail. Now, if people are new and these AWS summits, we see them as education. First of all, there's sometimes a bit confused about those instance types because the naming schema is getting more and more complex. So if we have an instance type with the name P3DN24X large, what it means is, first of all, the P is the instance type. Now it's the general purpose GPU instance. It's actually the most powerful instance with GPU that you can have in the cloud. Now the 3 is the version number. That means there was a P1, P2 before. And the DN, they are the D and the N, they're additional capabilities. So just imagine D for disk and N for networking. This is how I remember it. And it actually means that there is a high-speed, low-latency NVMe-based SSD that is physically connected to the server. That's the disk. And then there is 100 gigabit per second networking. That's the N for the networking. And then the 24X large, it means that's the large instance size. It's the 96 vCPUs, 256 gigabyte of RAM, and 8 NVIDIA V100 graphic cards. So looking at those 3 instance types that I already told you I want to emphasize a little bit on, the P3DN, I basically explained with the naming schema. You can guess, since this is the most powerful GPU instance that we have these days, this is ideal for running distributed machine learning workloads. So machine learning workloads on AWS, it's typically SageMaker. This is where you have the Jupyter notebooks, or you could use it to start to spin up the deep learning AMIs that we provide. Again, it's 96 custom vCPUs on a Intel Xeon scalable processor and 1.8 terabyte of disk. And it comes with support for this elastic fabric adapter, and that's what I called HPC class networking that we offer. I'll come back to this later. So this is like a really super powerful instance for machine learning. This is the takeaway. Now, there is another one that is kind of very, very different. It's called Z1D or Z1D, depending on where you learned your English. And as I told you, we have this Amdahl's law that says like every 18 months the processing power is doubling. And for a long time, the clock speed of the CPUs, they were increasing a lot and doubling, but this is kind of terminated now. So what we see these days in processor, in CPU architectures, is that we have more and more cores. And that's the general trend that we see. Now this instance, and this is why I kind of emphasize on this, is very different. It doesn't give you more cores. It actually gives you relatively few cores. If you look at, there is an 8:1 gigabyte to vCPU ratio, which is very, very little. But the cores that you get, they support a sustained throughput of 4 gigahertz, a sustained clock rate of 4 gigahertz. Now you might sit there and wonder, why is this the opposite of what we see as a general trend? No, why do we actually give you this instance with relatively little cores and a high sustained clock rate? Now the answer is there is legacy applications like databases that you know from on-premises, where you pay per core, where people prefer not to have that many cores, but for the cores that they have a consistent high throughput. And this is why we have this Z1 or Z1D instance. People like it a lot to run Oracle databases on this instance type. Right, then we have a C5N. Remember the N, that's the capability for networking. 100 gigabit per second networking. So that's the perfect instance to unblock any network-bound workloads where you need more than 25 gigabit per second or more than 50 gigabit per second. This is what you get on this C5N. And you should make sure to update to the latest ENA drivers. And again, it supports this EFA, the elastic fabric adapter. And very interesting instance type. It's not an instance type, it's actually a capability again. It's the AMD EPYC processor that we give you now as a second choice to a classic Intel processor that we used until now. So for the instance types like the M5 and the R5 and the T3, there is now a M5A and the R5A and the T3A. And the A, again, is this capability. That means you can have it with an AMD processor. Now, the AMD processor, it's application and instance size compatible. That means there is no migration necessary. So the same workload will basically run on this instance type with the A capability, but there will be about a 10% cost saving. Now, 10% cost saving, again, sounds a lot like sales and marketing. We typically encourage you to do your own benchmarks, to do your own measurements. But the important thing is that here you get this application compatibility and you can just continue to run your classical workloads. And I'm pointing this out because there is another one that looks similar, and this is where we use the uppercase A for the A1 instance type, but it's not similar at all. It's actually using an ARM processor. That's the processor that you all know from your mobile phones. So between the line on this slide, it says that the processors that we know from Raspberry Pis and mobile phones kind of made its way into server class computers. Now, the important thing, this ARM processor, it's actually very energy efficient and it's still powerful. And at the end, you will have a 45% cost saving. So the important thing here to remember is that this is not application compatible. So you probably will never, well, not today, I don't want to say never, but you will not run your SAP or Oracle workloads on this processor because it's just not binary compatible. The question is, why do I highly advertise it then? And the answer is, if you go to other presentations, you see that the age of microservices is now. No, people blow up their monoliths and they have dozens or hundreds of microservices. And if you're in control of your own software, if you build it and deploy it, then of course you can use these processors and scale out in a really nice way and get this 45% of cost saving. So there's different kind of workloads that we expect to run on these instance types. So you've seen that basically we want to give you choice. No, we have Intel processors. I talked about the GPUs that come from NVIDIA. We talked about AMD. The ARM processor is a custom processor that we designed and we built. And then there is one more. It's also custom designed and custom built processor. It's called AWS Inferentia, and it's a custom processor built to run machine learning workloads in parallel. This is what we do these days on the GPUs, but the Inferentia processor that we are currently, that we announced it, will run the same workload with about 10% of the cost. So it's a custom-built processor to run machine learning workloads. So the idea is we want to give you choice. That's why we have all these different options, and we don't want to lock you in. You can choose and pick the best processor for you. Again, remember how I started this presentation when I told you there was this time when PhD students spent 4 years working to adapt their workload to a certain machine architecture. I think this is completely gone. Now you pick the right processors. Even if you explore them, if you need to try and see if they're working, you can do this in parallel, and then you select the best one and you keep the best one. Now, I was talking a lot about the EFA, the Elastic Fabric Adapter, which I think is a major breakthrough in doing HPC in the cloud. So the Elastic Fabric Adapter, or short EFA, allows you to solve actually the latency problem, and that's super important to understand. In computer science, it's relatively easy to increase the bandwidth, no? So you see we've gone from 25 gigabit per second to 50 to 100. But it's kind of very hard to reduce the latency. Imagine doing this yourself. If you need to increase the bandwidth, you can always have another network card, another cable, and you have twice the bandwidth. But to reduce the latency, sooner or later you hit problems that come from the operating system, that come from the TCP/IP stack. Now, people say, well, but if it's the operating system and the TCP/IP stack, what can I do? Can you live without it? Well, not really. But you can kind of make your way around it. And this is exactly what the EFA is doing. So it's bypassing the TCP/IP stack and the operating system. And it allows you directly to access this HPC class of interconnect. And now you might say, but then if I have no TCP/IP and no web browser and no Outlook client, what can I use it for? Well, people obviously don't want to use it for the Outlook client. They want to use it for MPI. I guess most of you know MPI. That's the classic way to program HPC computers with message passing. And I think it's been around for more than 20 years now. And it still exists. It's still used a lot. So if you use MPI, you have your applications written to MPI. They use the MPI library. And then the MPI library is using a library which is called libfabric, which is doing the magic, which is bypassing the classical TCP/IP stack. But it doesn't mean that the machine is not accessible via TCP/IP anymore. We still do both. So this is one way to run your MPI applications. And because we have this direct access to EFA, we get very low latencies. And even more important, we get consistent low latencies. That's the other thing that is kind of disturbing a lot if you look at algorithms and scalability. If you have low latencies, but then you get jitter, the latency itself, even if it's low, it goes up and down. So we get consistently low latencies with very little jitter with this EFA. And this is why I think this is a very important breakthrough. So normally you have your application running on top of MPI, which is using the TCP/IP stack, and then the classical network card. And now with this new EFA, there is the MPI implementation that is using libfabric. That means to your application, you basically see no difference. You can run the same application on top of this EFA kernel driver that is accessed by the libfabric, and that is then accessing the EFA device. So I think this is a very important breakthrough that you should remember. Talking about file systems, I already explained you the different options that we have, like S3 and EBS and EFS. And again, there was a major breakthrough. It was announced last year at reInvent. It's available now. It's called Luster. For those who haven't used it, it sounds like a strange name. It's actually a combination of Linux and cluster. This is where the name Luster comes from. It's a POSIX compliant, high performance file system. And it's actually very efficient. It gives you sub-millisecond latencies, and it's possible to do this because it's running in parallel. It's a parallel file system, and it's backed with SSDs. And the more storage you have, the more throughput you get. For every terabyte of storage that you add, you get another 200 megabyte per second of throughput. So the amazing thing is it scales linearly. The more storage you give it, the more throughput you get. So FSX is like a family, like an umbrella that we created for running managed third-party file systems. And there is FSX Luster, and there is also FSX Windows for the Windows people. So it's managed third-party file systems, but the important one here is the Luster. And another nice feature that I just quickly want to mention is that we can initialize such a Luster file system. Basically, you create it, and then you mount it with -T Luster, and then you can have it initialized with a S3 bucket. That means all the objects in the S3 bucket are already visible in your file system. Then you do the compute, you do the I/O with the low latency, and then at the end it's written back to S3 if you want. There's blog postings available where you see how to do this. It's actually quite easy. You can create it with the command line. You can create it with the admin console. And the nice thing is it can be initialized from S3. Right, so one more thing that I want to explain, and I want to explain it because I think you might know it already under a different name. It's called AWS Parallel Cluster. That's the new name, and the previous name was CFN Cluster. It used to be an open source project that got more and more popular, and this is why we put some resources, some engineering behind, and somebody believed it should have a new name. This is why it's called AWS Parallel Cluster now. And it is basically a set of Python scripts that you install with a pip, and then you have a command line, and you can use a pcluster and a configuration file that defines criteria of your cluster, like which scheduler do you want to use, SGE or Torque or Slurm. And then you start, you create, you start, you shut down, or you update your cluster. So this is a very nice, convenient way where you basically, I did it the first time, I needed like 20 minutes to set up a cluster. And a lot of this was reading, so if you do it again, you can probably script it and do it in a few minutes, where you have this command line and then get easy access to a HPC cluster that has a scheduler pre-installed that you can just use, and you define what instance types you want to use. So this was the technical overview, like picking out the cherries and telling you about all the new things that happened last year. And now I want to hand over to Sebastian. Sebastian is really doing HPC in the cloud. So he's a user, he's a customer of ours, and he's going to explain you how they use HPC in the cloud for genomics. So welcome, Sebastian.
Thank you. Okay. Hello everyone, my name is Sebastian Wasilewski. I'm a technical project manager working within the Center for Genomics Research of AstraZeneca. And I would like to show you how we use the AWS technology stack in order to build and operate something which is probably one of the most efficient and fastest genomics pipelines in the pharmaceutical industry. So, the Center for Genomics Research is in the core of AstraZeneca Genomics Initiative. It was established in 2016 with the goal to generate genomics data and analyze it by the means of advanced analytics, jointly with a vast amount of clinical data, in order to build new biological knowledge that will then inform our research strategies, business decision making, including things like identifying new drug targets, so those are the targets for new future medicines, or providing mechanisms for validating the existing pharmaceutical targets using genomics information. The goal of the Center for Genomics Research is the way we are approaching this is to analyze data from up to 2 million individuals. Half a million of that group will be coming from our internal clinical studies. It's an unprecedented scale for genomics research. No one in the industry has done genomics research of this scale before. So why are we doing? So the first key thing here is that having that data will allow us to understand more about the disease, underlying biology of the disease. And there's a lot that we don't know. It will lead to new new drug targets. And those are the targets, those are the underlying scientific basis for the future medicines. It will also allow us to improve the diagnostic methods. And the diagnostic methods then can be used, for example, for supporting of how we select participants to clinical trials, or in the future to match therapies to patients in the way that are more likely to benefit them. So we started in 2016, and we immediately encountered a number of challenges. So when you think about that scale of the data, of course the first challenge is the volume and the compute itself. But then we also, at that stage, we didn't know how we are going to receive this data, what the schedule is going to be, how big the batches will be. So we needed a solution that can scale up and down depending of the needs. We also knew at that stage that whatever we know in 2016 about how we want to analyze the genomes, what are the best practices, gold standards in analyzing genomics information, might not be exactly the same as it will be in 2019 as it is now, or in 5 years' time. So we need a solution that we can first control, and secondly that it can evolve, it can be adapt to the needs, and it can evolve along with how our knowledge about this data and how new analytics and data processing methods evolve. On top of that, we're looking for a platform that will allow us to process this vast amount of data in a way that is efficient. In a way, we're talking about storing it, we're talking about analyzing it and then reusing it, being able to find it in a number of years. So that was one of the key requirements here, that we knew that that it's not one-off exercise. We knew that we'll be accumulating this data and we will need to be able to deal with it in an efficient manner. So we made a decision to build on top of the AWS platform, and we actually did it. So we built the pipeline. There are few, so our pipeline is here, you can see it at the top. There are few key parts. I'm not going to go through all the steps here. I want to highlight a few things. So as you can see here, the first part at the top is split into three things: the primary, the secondary, and the tertiary. Now, I'm going to stop here and talk a bit more about what this pipeline really does and why this is done this way. So, when you think about sequencing, I mean, the journey starts with the sequencer. So, the sequencer is a device that takes a biological sample and converts this into a series of reads. Now, what those reads are, you can imagine you have a genome and you have a short, so genome is a long thing, and imagine you have a short window that at one moment your sequencer can only read that window. And imagine you sampled your genome with that short window and you go up and down. It's pretty much a random process. So you randomly take the window and sample your genome. What you get from that is something we call unaligned reads. So we know that we covered the genome, we just don't know exactly how it is aligned, and we know that this is highly redundant data set. So then the next step here that we need to do is all around the secondary analysis. So the secondary analysis is about taking the unaligned reads and actually reconstructing the genome itself. So we do that computationally. It's a computationally heavy process. It takes a lot of disk space first, a lot of RAM and compute, and I will show you some statistics in a moment. And then after we reconstruct the genome, then the next step is something we call variant calling. Now, variant calling is nothing else like taking your genome and looking, okay, what are the mutations that are specific to this genome? So as you know, if you compare genomes of people who are in this room, we will all have some mutations that are specific to us and that actually define us as a person. So we look for those specific mutations for every single genome we process here. And this is something that is a key thing here, because this mutation information is something that people who do genomics this is our bread and butter. This is the key information that genomics research processes. So saying that, once we identify those mutations, what we do with them, we put them in a database. So we use Aurora MySQL database for that, and we deposit those mutations there. And then we connect the analytics engine. So this is the tertiary analysis. So tertiary analysis is all about stats. So we connect the analytics engine to the Aurora database and we mine the data. And there's a whole range of approaches you can use to mine that data. Don't want to go into that. I want to take a step back and look into how the pipeline has been architected. So as you see from the icons here, we rely heavily on serverless solutions. So the pipeline is defined using step functions, and then we use something called Lambda functions, or sorry, Lambda, AWS Lambda, in order to execute the steps. Now, some of the steps are longer or require more resource than what Lambda can provide. So for those, we use AWS batch. So we basically throw this heavy compute in the AWS batch. And batch creates EC2 instances of the appropriate type as needed. And one of those types is actually an FPGA accelerated unit. So we also use FPGA, which is a specialized microprocessor that in this case is designed to do some, to speed up some steps of the secondary analysis process. And the interesting thing around this one, around this approach, is that just before this talk, I went to our tech lead and asked, actually, do we have a single EC2 that runs constantly to support this? And his answer was no. There's no EC2 that we keep up and running all the time, because it's all auto-scaling, it's all on demand. And that's actually great, because the way we get the data, we get it in batches. So there might be nothing coming for most of the month, and then there is a batch with data that hits us. And this is something that actually we have happened end of last year. So in December, we got the first, let's call it, production batch of data. So we went live and operational in December, and we got the first 100,000 exomes. Now, exome is a coding region of genome, so it's basically an extract from the genome, it's a subset. So we got this 100,000 exomes, and we observed that it took 100 hours to process. So this is actually incredible. When you think about a few years back, people would think that, oh, this is not possible. So at this stage, I think we have here one of the most efficient, if not the most efficient, pipeline in the pharmaceutical sector. So I've been telling you that this 100,000 exomes and this genomics data in general is large. And some of you might deal with large data, and I'm pretty sure that there are some fields that produce more data than what we have. But from the genomics perspective, I can show you what is that we consider large. So in order to do 100,000 exomes, this required almost 1 million batch jobs. If you take a snapshot of what we've been doing of the state of our virtual cluster, at any time during that, we were running at slightly over 7,000 virtual CPUs at the time, and the concurrent memory, so memory between those cores, was around 23 terabytes. We processed 0.5 petabyte of data. So this 100,000 exomes accounted to 0.5 petabyte of data, and the result of that, those mutations that I told you, those result was 4 billion entries into the Aurora DB. Now, I told you at the very beginning of this talk that we are aiming 2 million genomes. So now our aim is 20 times what you see on the screen. So it's actually massive. So where does it put us? What the next steps are? So now having the data, having the pipeline operational, we start looking into interpretation of the data and digging more into making the information there available to a wider group of AstraZeneca scientists. We also have a new target. So our target for this year is to do 4 times what we did last year. So to actually run 400 sequences. But all of this needs people, the right skills, the right talent. So we're also growing the team. So if you are a HPC cloud expert and you are interested in genomics research, please do talk to me after the call, after the meeting here, or find me on LinkedIn, or just go to the job site of the AstraZeneca website. Thank you.
Thank you, Sebastian. I think that was a really impressive talk, not only about HPC, but about processing very personal data, actually the most personal data that you can have, your source code, your genome. So with this, I want to close. I think the conclusion is that HPC in the cloud on AWS is like a whole new area. It gives you all the configuration options, all the flexibility, all the scalability that you ever wanted, that I never had when I was working in classic HPC on premises. And you now have it at your fingertips. So go and use it, go build something amazing. I have some references for you on the slides. There's actually pretty good recordings from reInvent. The slides are on Speaker Deck. They will be distributed here from AWS. The most important favor I ask you is to rate this session. You've seen the QR code, and we will display it again. And it's super important for us. We're a very number-driven company. If you like the topic, if you like the presentation, go and please rate it. This is how we can make sure to have a similar topic maybe next year. So get the app via the QR code. That's the thing that we look at. There will be a survey later asking you about general things, but the core rating is done via the app. So please use the app. With this, I want to say thank you. Thank you again to Sebastian for being such a great presenter. You have my details here. If you have more questions, there's colleagues of mine from the service team. We have solution architects. Please come and chat to us. We'll be around. I'm not walking away. I'm here the whole day. Thanks again. You've been a great audience. Thank you.